Right, so I'm Nguyen. I'm from the MIT Kavli Institute, the Institute for Artificial Intelligence and Fundamental Interaction at MIT, and also affiliated with CCA at some points. I'm here and super excited to talk to you about FLORAH, our algorithm to blend better multitrees with deep generative models. And I work on this with our amazing collaborators, Gerard Modi, Aaron Nguyen, and Rachel Somerville at CCA. All right, so let's get started. Once I figure this out. Oh, yeah. Okay. All right. So let's start it by giving ourselves a little bit of background and ask ourselves, how does an astrophysicist typically plant a multitrees? Right. So multitrees, what are multitrees and why are they important? So if you're like me and you care about the physics at the scale of the Milky Way, multitrees are super important because in the galaxy formation hierarchical models, multiple galaxies merge into one galaxies. And in the case of the Milky Way, the potential of the Milky Way is very sensitive to what galaxies merge into the Milky Way at what redshift. Multitrees are also important on a large scale. And if you like me, you also care about the physics on a large scale. And you can have very simple multitrees like the one that we have in the Milky Way, mostly because we don't have enough data, or you can have massive multitrees like in these kind of simulations. And why are those multitrees important? Those multitrees important because you take the dark matter and body simulation only multitrees, galaxy multitrees, and you add the semi-analytical models, and bam, you have galaxies simulations. So how does an astrophysicist typically plant a multitrees? So there are two ways. One way is you can use n-body simulation. You can run a cosmological box such as Illustris, and all the amazing simulations that people mentioned today. And you can use Rockstar Halo Finder to extract them, and you can from the dark matter particles, and you can connect the halo. You can connect the dark matter halo using algorithms such as consistent trees to get a multitrees. And a second way that you can do this is you can use extended spread-factors formalism. And the way you use it is extended spread-factor gives you the conditional probabilities that given an initial halo at the initial mass, like what is the mass of the halo at a certain redshift. And you Spread-factor's equation plus some assumption, you can have yourself a bunch of multitrees. So what are the pros and cons of this method? For the n-body trees, you can think of them as the truth multitrees that are typically very accurate. Why do I air quote the truth? Because there are some caveats, because they're dependent on the algorithm that you use to extract the halos from the dark matter particles and the algorithm that you use to connect this halo together. The disadvantage of n-body simulation trees is that n-body simulation, as we know, is very slow. It's very difficult to explore different cosmological parameters. And it's also very difficult to capture a wide range of molecular dynamics. Like say, for example, it's hard to have a simulation that can simultaneously capture the mass of the faintest dwarf galaxies to the mass of galaxy cluster. And for extended spread-factors, they are typically much faster compared to n-body simulation, but they're not very accurate because they require many assumptions. For example, they require the Markov properties of the, like in the spread-factor equation. And they also does not take into account a lot of other properties of the halos. They cannot take into account, for example, the concentration, the other environmental properties of the trees. Right, so inspired by this, we create our own algorithm and we call it FLORAH, and I will explain the acronyms later. So I want to reiterate what the objectives, what we're planning to do, and what's our approach. So our objectives is that given an initial halo, let's say I give you a Milky Way at a certain redshift, I want to generate multiple ensembles of multitrees, multiple realization of the multitrees with properties consistent with n-body simulation. I want to stress the ensemble part because multitrees are inherently random. If I give you another galaxies, another Milky Way, that Milky Way will not necessarily have the same merger history of our own Milky Way. For example, it might not have a large Magellanic cloud. And for the first approach, we will model the merger trees. We will only try to model the main generative branch of the merger trees, which keep track of the most massive halos of the merger trees. And we're going to model it as a sequence. So we're going to use machine learning to solve this problem. And for the sequence part, we will use recurrent neural network to model it. And for the ensembles part, we will use generative models. In my case, anomalous and flow. So which come to our acronyms. FLORAH, flow-based recurrent models for assembly history. So how does FLORAH plans the merger trees? So first, I want to tell you about something that I've been kind of recently obsessed about, and it's on the news, and you might have heard of it, which is called ChatGPT. ChatGPT is the AI language models. When you give it like some kind of prompt, you ask it a question, it put into some kind of black box that it does, let's give you an answer. So why do I want to even talk about ChatGPT? Because ChatGPT is a conditional generative model. It's not just generative models. I don't just want to generate anything. I want to generate something, given something. In the case of ChatGPT, you have to give it a prompt. Without a prompt, ChatGPT would not work. So for our case, our prompt or question for the models is the galaxies. And in particular, the initial virial mass and the initial concentration for the galaxies. And we're also going to give it a list of scale factors that we want the merger trees to be generated at. We put it into some kind of neural network models, and we end up with a merger trees, which is the virial mass and the concentration at each of the scale factors that we give it. First, I want to talk about the embodied simulation that we use. So we use two big simulations. One is the very small multi-dark Planck, and the other is the graph simulation. Graph stands for gadget at ultra high redshift with extra fine time step that is run by Nguyen at NASA Goddard. And the paper is still in prep, and it should be come out in a few months. And the reason I want to use multiple cosmological box is, as remember for embodied simulation, it's hard to capture a wide range of merger dynamics. You don't have simulation that's covered from redshift z equal to 0 to redshift z equal to like 20, redshift z equal to 50, with like enough resolution at the higher redshift. And also you don't have enough resolution in terms of the time step as well. So for example, if you look into this graph, you can see the time step of graph versus the time step of very small multi-dark, Bolshoi Planck simulation, and the lustrous TNG. And you can see that graph has extremely fine time step. And one of the reasons that I want to use graph in conjunction with very small multi-dark is that if you look at here, this is the mass accretion history of the main generative branch as a function of redshift or age of the universe. And here I plot the virial mass, and each of the curve, each of the trees here, and basically plot the median accretion history. And you can see there's significant overlap between the graph box and the very small multi-dark box at redshift from roughly 6 to 8. So using this, we can combine these two simulations and then create a merger trees and then train an algorithm that can get a merger trees from z equal to 0 to z equal to 20. Though in this presentation, I will only show very small multi-dark, but you can ask me about the combined box later. So for the training process, we want to start with an input. So the input is going to be the properties of our galaxies. Let's say we extract a bunch of trees out of your embodied simulation. You have a bunch of log virial mass, a bunch of concentration, and you have the scale factor at each of the snapshot. And I also want to stress that we're training on iso trees only, which means that we take away all the subhalos of the trees. We don't deal with subhalos here, or yet. And then I shifted the input. I put the initial input x0 and t0 into some kind of box, and this is going to be our neural network. Get some kind of feature extractor, and then I feed this feature extractor into a normalizing flow. And then I compare the output of the normalizing flow with the next time step. And I want to stress also that we train the normalizing flow and this neural network simultaneously. So how does this neural network be able to remember the properties of a tree, be able to remember the accretion history of the trees. So spoiler, this is a recurrent neural network, so it has a hidden state. So this hidden state is gonna get memorized, gonna get carried along. So we're gonna repeat the whole procedure for the next time step, and we keep repeating the procedure for the entire trees. And the final loss function will be the sum of all the loss function for each of the time step. So in doing the generation process, things works a little bit differently. So for generation process, you only have the time step, right? You only know, like what kind of scale factor you want to have your output on, and you only know the initial information of the halo. So for this, we basically work basically the same. We put the initial information of the halos, the initial scale factor to a recurrent neural network, spit out some features. Using normalized flow, we sample the properties. We sample the properties of the halos for the next time step called x1 hat. And for this case, we copy x1 hat to the next time step and repeat this procedure. And the hidden state, which we initialize to be all zeros, will carry along. All right, so let's show some result. And if you're interested, the top images is the AI generated image, which lead me to which of these trees are AI generated trees. And to explain the plot, I'm plotting the redshift versus the mass, and this mass is normalized by the initial mass. And the initial mass here, I bin the initial mass from 9.5 to 10.5. And this line here is basically the 64 M dark matter, which we define to be the resolution at which the halo is no longer considered resolved. So the red one is the one that is AI generated. So the trick here is that the merger tree from the real merger tree they terminated, but in this case, I forgot to make them terminate randomly. And you can kind of see, so using the same network, so this is using one network, I plot the same graph for different mass bin, and you can see that it looks very much the same. And this is only the main progenitor branch I want to stress. So a better way to plot this is that if you take all the bins, you take the median and you compute the 68 percentile and the 95 percentile band, and you plot them as a function of redshift. So, and the red curve here, is FLORAH, and the blue curve is the simulation. And as you can see, that things start to deviate it, like after the resolution. Like after the resolution limit, mostly because we use the concentration, and after 64, below 64 M dark matter, the concentration is not very reliable. And the residual from the median, from two of the median curves subtracted for each other's. And the limit of the plot, the minus 0.25 and the minus and the 0.25 is roughly a factor of 2 in terms of like log 10 scale. What's actually interesting is that I didn't realize how faint it is, but if you can see the shaded region, the neural network has never seen the shaded region. Like everything after the shaded region are extrapolation. That's why you see that it fails in some case, but for some case it actually works. Most of the time it fails because of resolution limits as well. And because we also train on the concentration, we also predict the concentration. I also want to show the same plot for the concentration. And as you see, that they work typically very well. One thing that we want to check our trees, we want to check if the merger history works. So for this figure here, I plot the formation time distribution. So I compute the Z25, which is the redshift at which the halo from 25% of its mass, Z50 and Z75, and each of the row is different mass bin. And I compare the distribution that is outputted by the FLORAH tree, and I compute the distribution that's outputted by very small multidark, and you can see that they are very identical. And I also plot the formation time versus the concentration, but here I use a scale factor instead of redshift. And this is for Z25, Z15, Z75. I use scale factor because this is what people typically use when they look into formation time versus concentration. And I plot the median 68 percentile and 95 percentile. And you can see that it successfully recovered a lot of formation time distribution. So another thing that we do to test our trees is we use Santa Cruz SAM. And we take all of these trees, feed into Santa Cruz SAM. We take all the very small multi-dark tree, feed into Santa Cruz SAM, and we also use only the main progenitor branch so that we can have like a faithful comparison between the two trees, the simulated trees and the FLORAH trees. And as you can see here, I plot the stellar mass and halo mass relation, each of the data point individually, as well as the median and the 68 percentile. And you can see that they are pretty much identical. And here I plot the residual of the stellar mass, halo mass. So basically the spread in this plot. And I plot it against the concentration, and it shows a correlation between this concentration and this residual, the same correlation that you see in M-body simulation. And this is basically how you kind of prove assembly bias. And one thing that we also do is we take all this tree, so we don't predict position, but you can like just assume, like you can like just like assume the position similarly to like the initial distribution. But with different trees, different merger history, you will have like different mass, right? You have like different stellar mass, and if you plot the power spectrum density, like the power spectrum of the mass, you don't expect them to be exactly the same. Yeah, so here I plot the power spectrum from FLORAH, from very small multi-dark, for a sub-box, like for sub-box of very small multi-dark. And here I divide, this is still the power spectrum, but I divide them into a late forming and an early forming population. So with the 25% earliest forming and the 25% latest forming, and plot them together, and you can see that they are very consistent between very small multi-dark and FLORAH. And on top of that, you can kind of see this assembly bias. All right, so for future work, what do I want to do for future work? So the first thing that we want to do is we want to combine the box. So I only show you the result from very small multi-dark, which span from z equals 0 to z equal roughly 6 or 8. And the next step is to combine in the box. And I have some initial result for combining the box that I got pretty much this weekend. And I kind of put it here, have a zoom in of this plot if you're interested in seeing that. But I haven't really do a lot of tests on this yet, so that's why I didn't want to talk about it today. And the second step that we want to do is we want to also include secondary branches and, you know, like the entire merger trees. You can see here that right now we only predict this very thick black line, but we want to predict everything here. And I have some plans for that, and you can still use recurrent network if you model the branching factors properly, or you can also use a graph generative models. And the next step is that you want to do is you want to also condition the trees on the cosmological parameters so that you can like explore different cosmological parameters. And for this, we plan to use Camo. Another thing just kind of like on top of our head is that we're trying to apply this on particle mass simulation, but we haven't really thought that much about it yet. All right, so I'll put a summary slide here. If anything I want you to remember from this talk is FLORAH, flow-based recurrent models for assembly history. And we developed this generative models, generate main progenitor branch of merger trees, and we show that successfully recover the population mass and concentration history. And if you add the trees to the Santa Cruz SAM, it also successfully recovered things such as the stellar mass relation, assembly bias. And my contact information is here. Yeah, and I will take any question.
Hi, Trey. Very interesting. This is Martin Ray. Do you have a metric that you can define for me to understand how much better this is compared to just using the analytics from EPS to generate trees?
So unfortunately, I don't have the projector trees with me, but I think typically projector trees can deviate it like up to like factor of 2, which like say for example in this case it would be like
sorry, in which
it would
case?
be like at the edge of the residual plot. It will like go to the roof of this residual plot.
Okay, thanks.
Cool, Elise Dareford. Great talk. And it seems like this is working really well, but you know, the first slide just made me think of transformers, and I was wondering, was there a reason you picked RNNs over transformers?
Yeah, so I even make a comparison with ChatGPT, and ChatGPT uses a transformer. We tested on a transformer, and the thing about transformer is they are really hard to train and also really slow. I made a transformer work like using a similar scheme, and it worked like roughly, the performance roughly similar. It's a little bit worse for the transformer, but it's probably due to the fact that it's probably not converged entirely yet. So for now, we kind of just resort ourselves to recurrent neural network. So for our case, it's actually a gate recurrent, gate recurrent unit. Yeah. Cool.
Johnson Ting here. It seems like it's great work. I'm just thinking like you should be able to test more stringently than, because like the statistic that you show here can also be like done quite well with a semi-analytic models. I think the gain here, what you can do is to join a distribution, meaning that you can look at the correlation between the subsequent like redshift, which is not shown here, I think, right? So here is just like drawing from like the marginal distribution. But have you checked the joint distribution like between steps?
I have checked the 2D distribution between the mass and the concentration.
Like between time steps, so like M1, M2. So the same if you follow the track. Yeah, it's more than just the marginal distribution, but it's rather the whole track, right? So you can check that. You check that?
Yeah, so I have already checked that, and it's consistent between very small multidark and FLORAH tree. I didn't show it here because it's basically a chain corner plot.
Yeah, and then again, like compared to Trinity, it's really the non-Gaussianity, because you can like model the outliers. Seems like it's a more stringent test if you look at the upper percentile, not the bulk of the track, but rather the tail of the track. So have a look at, you know, like the 95 percentile, like do they still agree well at the tail of the distribution?
I think so. The only other test that I did is that I did like plot the entire distribution of the mass for the entire population at each of the redshift. I don't think I've checked what you said yet, but we should definitely talk about it.
Yeah, it's a very powerful tool. I'm pretty sure like you will also agree in those statistics, but those are the things that cannot be done with a more like simpler models. So it'd be great to check.
Yep, thank you.
Okay. So yeah, thanks for the talk, Tree. It's super cool stuff. I don't know if this is something that you looked into, but you know, real merger trees have a lot of scatter in them between epochs. And with this, do you end up kind of implicitly assuming that that each halo always evolves smoothly, or do you find any kind of merger events in the trees that you make?
So what do you mean by between epochs? Do you mean like between snapshot or between epochs of the, okay, between snapshot? Yeah, so one thing that I didn't have time to mention for the merger trees is that like we do have a pre-processing step for the merger trees. And typically when, if you look at like a merger trees, you will see that it's jumping over place. And sometimes you can have a trees with the mass constantly larger than the initial mass, because sometimes like consistent tree doesn't track the halo correctly. So we decided to not post-process any of that, pre-process any of that. So when I feed in our training data, there are trees that or like jumping all over the place. And the reason for that is that we don't want what the network learn depending on what I used to like pre-process. And if also pre-processes is really like pre-process them really take a long time, and also like does reduce the training data set a bit if you have to throw away a lot of the trees.
Sure, but do you then, like in the merge trees that you generate with FLORAH, do you see that jumping around between between?
We do see it jumping around. Like say for example, this little guy here,
Yeah.
you can see that it's jump a little bit. Yeah, because like what FLORAH do is that it's trying to mimic this distribution, so it will mimic whatever consistent tree give it, and whatever rockstar give it. So another disadvantage of like the way that I'm doing it at the moment is that it does depend on how consistent tree define, like how rockstar define a halo and how consistent tree depending on the tree, and we have not tested on different kind of algorithm, different kind of tree finder, halo finder algorithm yet, but that's like our plan in the future.
Thank you.
Thanks for a very nice talk. This is Peter Brucey. I really like where you show the new results that blow APS out of the water. So I had a question about secondary halo properties other than concentration, because we know that assembly histories of halos might depend on more than concentration, like shape or other things. Have you thought about including other properties too?
Yes. So we plan to include other properties. So when in one of the steps, especially the secondary branches here, so here we are able to capture somewhat the assembly bias because we use concentration, and concentration, like you say, does depend on like the history of the of the trees. But when you include secondary branch, things might change. So we might need to like include other properties such as the environment of the environment, or like the shape of the halo, the spin of the halo. I did not include them here. And yeah, because right now we have a working model and we plan to at least get this man progenitors branch out, and then we're going to look into more properties. Also a thing is, I was trying to look into the environmental dependence using like some kind of environmental parameters to predict the trees, but graph is a fairly new simulation and all of that parameter hasn't been calculated yet. And it does take a long time to look into the particle data and compute. Then so like say for example, the n nearest halo or something like that. Yeah, but we will definitely do that in the future.
If there's no more question, let's thank Tree again.